Okay, so greetings everyone. My name is Aditya Sharma. I am from A2 section B1 batch. My roll number is 20, and this video is for my teacher's assessment 2 of quantum computing. My topic is classical and quantum billiard ball example. Now let's proceed. Okay, so now we're gonna understand this topic first by using the classical probabilistic system. Now, in the classical probabilistic system, all the probabilities are expressed in the form of real numbers. So now let's consider four vertices. Now, what I've basically done is I've just created some arrows pointing in the direction of which the particle can go in the next time interval. So, for example, the probability of the particle going from 0 to 1 is half. Similarly, the probability of the particle going from 3 to 1 is half. The probability of particle going from 1 to 0 is half. From 1 to 3 is also half. From 3 to 2 is half. From 2 to 3 is half. From 2 to 0 is also half. And from 0 to 2 is also half. Now, let us consider that the billiard ball that we're going to be using is initially placed at vertex 0. All right. Now, we'll find the adjacency matrix of the system. Now, to write the adjacency matrix, the adjacency matrix has the dimensions of n cross n, where n is the number of vertices. Now, in this case, we have four vertices 0, 1, 2, and 3. So I've just basically written 0, 1, 2, 3, 0, 1, 2, 3 in the columns for rough work. Now we have written the adjacency matrix. Now let me explain how we have written this. So how we basically write it is that we see the column. Now the column number is 0. So we does the particle is going from 0 to 0, from column to row. So from 0 to 0. Now the particle is initially placed at 0, and then it has 50% chance of moving to 1 and 50% chance of moving to 2. That means that it has no chance of staying at 0. So from 0 to 0, the probability is 0. Now from 0 to 1, from 0th position to 1 position, the probability is given by this arrow, which is half. So we have written half here. From 0 to 2, the probability is given by this arrow, and the probability is also half. From 0 to 3, as you can see, we cannot directly go to 3. Yes, we can go to 1 and go to 3, or go to 2 and 3, but we cannot directly go to 3. Since we cannot directly go to 3, the probability of going from 0 directly to 3 is 0. Now, similarly, the probability of going from vertex 1 to 0 is half. From 1 to 0 is half. Similarly, we have written all these. Now, let's move forward. Now, what we'll basically do is we'll operate the adjacency matrix on the initial state. Now, what this means is that after we multiply the adjacency matrix with the initial state matrix, it will give us a new matrix which will give us the probability of the particle's position in the next time interval. So now this first row represents vertex 0, the second row represents vertex 1, the third row represents vertex 2, and the fourth row represents vertex 3. Now, as already mentioned in the previous slides, the ball is already initially placed at 0, vertex 0. So the probability of it being at 0 initially is 1, and all the rest of the other vertices is 0. Now let's go next. So now we'll find the probability of the state of the ball after one time click. Now, what does a time click mean? A time click is basically a time interval. Now, it can be anything. It can be milliseconds, nanoseconds, it can be minutes, hours, years, even decades. It totally depends upon us to take what is the time click. In this case we are not going to measure any of the time click. We're just going to call it one time click. So now here what I've basically done is this big matrix is the adjacency matrix that we've written before. This one right here is the initial state matrix. So after we multiply these two by basic matrix multiplication, we get 0 into 1 plus half into 0 plus half into 0 plus 0 into 0. That all adds up to be 0. So the probability of the particle being at vertex 0 in the after the first time click will be 0. Similarly, half into 1 is half, plus 0 into 0 is 0, 0 into 0 is 0, half into 0 again 0. After we add all these up, we get half. So the probability of the particle the ball being at vertex 1 after one time click will be half. Similarly, the probability of the particle being at vertex 2 after the first time click will be half, and at vertex 3 will be 0. Now we'll find the probability of the state of the ball after two time clicks. Now to find this new state after one time click, we have multiplied the adjacency matrix with the initial state matrix. Now to get the state of the ball after the second time click, what you have to do is we have to take the adjacency matrix and multiply it with the new state that we got, not the initial state, but the new state. Let's see. So this big matrix again here is the adjacency matrix. Now this is the new state that we got after the first time click. So after we multiply, we get this matrix, which depicts the new state after two time clicks. Now similarly, we'll also find the probability after three and four time clicks. So this is the adjacency matrix. This is the new state matrix that we got after the second time click. So after we multiply, we get 0, half, half, 0. Now, if you look closely, this is the same matrix that we got, which was right here, the new state after one time click. So it's basically stuck in a loop now. Even if we multiply it again with the adjacency matrix to get the new state after four time clicks, you will see that we get the new state after two time clicks, same matrix. So what this basically means is that the system will toggle between vertex 0, comma 3 and vertex 1, comma 2. So it basically means that the system will toggle like this. And we will not be able to get back the initial state. Thus, the system is not reversible. Now, this happened because we were using the classic probabilistic system, which used real numbers to represent the probabilities. Now, we'll look at the same problem using probabilistic system. Now, in the quantum probabilistic system, all the probabilities are expressed in the form of complex numbers. What that basically means, we'll learn it. So first, again, consider four vertices. Now, write its probabilities. Now, you all might be wondering how I've written 1 by root 2 there. So we know that C into C conjugate is equal to mod of C square, where C is any complex number. Similarly, written psi into psi conjugate equal to mod of psi square. Now, mod of psi square represents the probability. So we know that the total probability will always be 1. So I've written mod of psi square equals to 1. So from this equation, we get psi into psi conjugate equals to 1. Now, when we take this particular complex number, when we multiply it, this is its mod square. So it's going to be half plus half, which is equal to 1. Thus, this is the complex number that we want to take for the probability. It's basically 1 by root 2 plus 0 iota. 1 by root 2 plus 0 iota. I have not written 0 iota there because there's no need. Now moving forward, again let the billiard ball initially be placed at vertex 0. Now we'll find the adjacency matrix again. We've already learned how to find the adjacency matrix. So it was initially placed at 0. So from 0 to 0, the probability will always be 0. From 0 to 1, it is 1 by root 2. From 0 to 2, it is also 1 by root 2. From 0 to 3, there's no direct link between them. Thus, it is 0. From 1 to 0, it is 1 by root 2. From 1 to 1, it is 0 because, of course, it can't go there. From 1 to 2, there's no direct link again, thus it's 0. From 1 to 3, though, it's negative 1 by root 2. Similarly, we have written the adjacency matrix here. Now we'll again operate the adjacency matrix on the initial state. So this is our initial state. Our ball was initially placed at vertex 0. So it's 1, 0, 0, 0 because it is only present at the vertex 0 initially. Now we'll again find the probability of the state of the ball after one time click. So this big matrix here is our adjacency matrix, and this is our initial state. Now, when we multiply this, we get 0, 1 by root 2, 1 by root 2, and 0. Now, this is the new state obtained after one time click. Now, we'll find the probability of the state of the ball after two time clicks. So, this is the adjacency matrix here again. This right here is the new state that we obtained after one time click. So after we multiply, we get 1, 0, 0, 0. Now, if you look closely, this is the initial state that we started with. The ball was initially at vertex 0. This also represents that. So the new state after two time clicks is actually also the initial state. So what we can infer from this is that we are obtaining the initial state of the system after two time clicks. Hence, the system is reversible in nature. Now, when we use the real numbers, when we use the real probabilistic system, when we use the classical probabilistic system, we were getting stuck in a loop. We were basically understanding that the system was not reversible in nature because we were using real numbers to express our probabilities. But using the quantum probabilistic system, after we express the probabilistic in complex numbers, we can see that the initial state of the system is getting returned back to us. That means that the system is reversible in nature. Thus, using the quantum probabilistic system, we can get reversible systems. That was it from my side. Thank you, everyone.